Hi everyone. This is going to be a lesson about optimization problems for Calculus 1. I think this is one of my favorite lessons for Calc 1. We've been looking at some applications of the derivative, and when I think of applications of the derivative, this is usually the section that I think of. So these are going to be some word problems using the derivative to answer some real-life questions. So let's go ahead and get started. So, what kind of word problems do I mean? So let's talk about some real-world problems. There are actually a lot of different types of optimization problems. We're just going to see a few of them in this section, but you'll be able to extend these methods to other types of problems as well. So, a real-life problem might be, let's say you have a small business and somehow you want to maximize profit. Or maybe you have a small business and you want to minimize your costs. Cost of doing business, cost of manufacturing something. Actually, on that note, suppose you're manufacturing something and you want to minimize the amount of material used. We'll have a problem like that, so you'll see what I mean. Or let's say that just in general in life you want to somehow minimize the amount of time or effort that you exert to do something to accomplish some goal. You still want to accomplish the goal, but you want to do it in the least amount of time or the least amount of effort. Or let's say you're constructing something and you want to maximize the amount of area or volume. I'm just going to say here, etc. These are some examples. And the thing that all of these have in common is that they have either the word maximize or the word minimize. And you know, lately we've been talking about finding the maximum value of a function or the minimum value of a function. So a key idea is that all of these are the absolute max or mins of functions. So we found maxima and minima by using the derivative, looking at critical values. And yeah, the idea is that there are going to be some word problems where we can turn it into a function, find the derivative, find where a minimum or a maximum occurs, and answer some kind of question. So most of this section is just going to be example word problems, but I'll give you some guidelines first. Some guidelines. These are called optimization word problems. We're trying to optimize something, whether it's in the maximum sense or the minimum sense. We're either trying to get the most of something or the least of something, and altogether we call that optimization. We're trying to find the optimal way to do something. Well, as a guideline, of course, you should carefully read the problem. I know that should go without saying, but you know, with word problems, you need to identify what is known and what is asked for. Because you don't want to be answering the wrong question. You don't want to be answering something that it didn't actually ask for. Another guideline is draw a diagram if it might help. I think a lot of these it will. It's usually up to us to introduce a function and variables. You should choose symbols that make sense. Choose symbols such as A for area, H for height, T for time, etc. Things that make it easy for you to keep track of things and make it easy for someone like me to understand what you came up with. By the way, I know we've done word problems in this class. This is just going to be a certain type of word problem. A lot of the advice here can apply to word problems in general. For these ones, we're going to want to try to write the function in terms of one variable. And then use methods we've discussed in recent lessons to find the absolute max or min. I guess I'll say in parentheses, in the domain. It has to be in the domain, right? Okay, that kind of goes without saying. So those are some guidelines, and the rest of this section is going to be example word problems. And I'll do a couple of them first, and then I'll have one for you to work on. And then maybe I'll come back and do another one. And I really think that with a new type of word problem, really the best way to teach you is by example. So we'll get started on one. I think we're going to see 4 of these. I'm going to say example 1. Suppose you have 2,400 feet of fencing and want to fence off a rectangular field that borders a straight river. I'll draw a picture of this. Let's see. You do not need a fence along the river. What are the dimensions of the field that has the largest area? Okay, so that is all that's given. This picture, this problem is not giving us a picture. I'm going to wind up drawing a picture as a part of solving this. But let's take a look at this. So we're given 2,400 feet of fencing, and we want to make a rectangular field. So there's more than one way to make a rectangle with 2,400 feet of fencing, right? In particular, this says that one of the sides of the rectangle is the border of a straight river, and we don't have to put a fence along the river. So we really only have to make 3 sides of this rectangle. So 2,400 feet, and we have to make 3 sides of a rectangle. The 4th side is sort of a natural border. It's a straight river. So I think if we're going to draw a picture of this, we should make it an overhead view because, you know, it's a rectangle as viewed from overhead. So let's first try to picture some possibilities. let's just brainstorm about this, okay? So I've got a river. Oh, let me get my blue pen for that. All right, the river is straight. I'll make it an approximately straight line, but let's say that's the river, okay? And one way that we could make a rectangle is we could make, you know, a fence go like this, and then have it go like this, and then come back down. And we've made a rectangular field where one of the sides is the river, right? And that's one possibility. That's one kind of rectangle. There's other possibilities as well. We could make one that's more maybe extends further away from the river. But if it extends further away from the river, then we used up a lot of our fencing to do that. So we don't have as much fencing to go horizontally anymore, so we need to come back down here. So it's not really as wide as the first example. And then another example to make a rectangle is we could make a fenced-in area that goes really far out from the river. But if we use a lot of the fencing to go really far away from the river, then we don't really have much left to go horizontally. So we get something that's kind of like a really tall rectangle. And I think that what's going to happen is if we try to compute the areas of these rectangles, I think that this first one is going to have a relatively low area because one of the side lengths is going to be very small. I think that the one in the middle here is going to be a better area. We're trying to get the most area possible. And then I think this last one is also going to be kind of a low area because, you know, you do length times width, and the width is very small here. So it's nice if you have kind of the perfect balance of length and width. And that's what we're trying to figure out. Maybe the best area might be to make a square. I mean, that's one type of rectangle. So if that's the best kind, then we'll find out as we do the math. All right, so that was just to help us visualize it. Now, in general, I'm going to draw one picture that I actually label. All right, so in general, let's draw another picture, and this time I'm going to label the side lengths. So here's the river. When I draw this, I have to assume some kind of shape, right? Just to draw it. So I don't know, I'll make it look a little bit like that middle picture. And I'm going to label the side lengths. What do you want to call them? I just called them X and Y. X and Y. You could call them A and B, whatever you want. Now, we want to maximize area. And what's the area of this rectangle? It's just one side times the other. We could say it's X times Y. And what is known? What information is given to us in this problem? The 2400. The entire amount of fencing that we used adds up to 2400. Well, how much fencing did we use? We used X plus Y plus X. So another way to write that is 2X plus Y. Has to be all 2,400 feet of fencing. If we're going to get the most area, we need to use all the fencing that we have. In some way, we're going to combine these, right? Now, in the guidelines that I gave you, I said that we should introduce a function and variables. We should choose symbols. And then the next step I said was try to write the function in terms of one variable. We have the area written in terms of two variables. X and Y are both unknowns. They both look like variables. So can we find a way to write the area? Here, I'll write some of this. We want A expressed just in terms of X. Not both. Not both. Not both X and Y. I mean, you could actually get a expressed just in terms of y, and that would be all right. The important thing is you get it expressed in terms of one variable. I think I'm going to choose x. So what we do is we use that second line. We know that 2x plus y equals 2400. Something like that has to be given in the problem, some information. And the 2400 and the fact that it's a rectangle and the picture I'm looking at, that's what helped me come up with this equation. And from this, we could solve for y in terms of x. And then we'll be able to substitute that in to the area equation. So the a equals xy can be rewritten as a equals x times this. And now we've done it. We wrote the area in terms of one variable, x. You can probably tell each problem that we do in this section is going to be a little different. This is a problem about area of a rectangle, and some other problems might involve different shapes, or they might not involve shapes at all. But I'm going to say for this one, the function we want to maximize is. So I claim that we wrote area as a function of x. And what do we do when we have a function? Like, a lot of times we call it f of x. I guess you could call it f if you want, but I think it's area. Let's just call it a. I am going to, however, I'm going to call it a of x. It's the area function where x is the variable. And I'm going to distribute this x and write it as 2400x minus 2x squared. All right, let's use the methods that we've discussed in recent lessons to find the absolute maximum. Like, where does a maximum occur for this? So we want to find critical numbers, right? Critical numbers or critical points. What you do is you need the derivative. There's the derivative. And then we set it equal, well, first we look to see, are there any places where this is undefined? I don't think so. So we set it equal to 0 and we solve. Solving this, you should get 4x equals 2400. So x equals 600. Now that's the only critical point that I've found, which makes me think it's probably the correct answer. But how do we know if a maximum actually occurs there? Well, we know how to find out. You set up a sign chart. You put your critical number on it, and you check something to the left of it and something to the right of it. So this would be a prime, this would be a. What we're looking for is a maximum for a. So we'd like to see this go increase and then decrease. If we see increase and then decrease, then we know we're good. So I actually checked a prime. A prime is 2400 minus 4x, so it's a relatively simple function. I put in 500. I could have chosen, maybe 100 would have been easier. But, 2400 minus 4 times 500, that's not that bad. It's 400, which is positive. I'm running out of space at the bottom here, but I'm just going to tell you that I checked 700 and found that it was negative. You can probably tell if you put 700 in, 2400 minus 2800. So we do get plus and then minus. So we get increase and then decrease, which is good because it means that the function is somehow going upward and then downward. So we do have a max occurring. So we verified, all of this work over here was to verify that x equals 600 is, in fact, an x-coordinate where a maximum occurs. So is that the answer, 600? Well, no, not really. I mean, go back and look at the problem. What did it ask us? It says, what are the dimensions of the field that has the largest area? If somebody said, what are the dimensions of a field? You don't just say 600. They would say 600 by what? So we need to find the other dimension. We found x is 600, so we need to find y. Now find y. Okay, well, this is going to be, let's see. We have up above something on our page I see we could use. Usually, if you review all the work you've done so far, you'll find something really helpful to help you get the other variable. Look at this. Y equals 2400 minus 2x. Let's use that. Y equals 2400 minus 2x. I got that from above. I'm going to move the page now. We can put in 600 because we verified that 600 is the x value where a maximum occurs. So 2400 minus 2 times 600, I wind up with 1200. So we already did the sign chart for x. We don't have to do anything like that for y. And in fact, we can say that we have found the optimal dimensions of the field, and it is 600 by 1200 feet. Oh, by the way, I'm not going to put a box around this yet. There's one more thing I want to do. Can I remind you what our picture looked like? Okay, this is what our picture looked like. We found that x is 600 and y is 1200. So, you know, I guess in an actual picture, you can imagine y needs to be twice as long as x, and that gets you the maximum area. So, in fact, it's not a square. And maybe it doesn't look exactly like any of the example rectangles that I drew, but that's okay. There's one more thing I want to include in this answer, though, is if somebody in real life was trying to build this fence and they said, I've got 2,400 feet of fencing, there's a straight river, I need to know the best way to make this fence. If you just told them to make it 600 by 1200, they still need to know which one is 600 and which one is 1200. See what I mean? Like if you just say 600 by 1200, it's like, okay, but which is which? Now, if you said x equals 600 and y equals 1200, that's still not really clear unless you also provided them with the picture. But like if you just said, oh yeah, make x 600, they would say, well, what's x? The problem didn't say anything about x or y. So let's do something like this. Let's say 600 by 1200 where the 1200 foot side is parallel to the river. Just including something like that makes it clear which is which. I like that. We could do a quick check. That in our picture, that if you do this, and this is 600, 1200, and 600, you can check that they do add up to the total amount of fencing that we had. 2,400. Good. I mean, of course, there's other combinations that also add up to 2,400, but that's one thing that you can check. Otherwise, you could go back and double check the derivative and, you know, that this was, in fact, a maximum. So we're done with this problem. As a side note, like we found the optimal dimensions, but I'm also going to tell you what is the max area that we get. Like, what if the problem asked you, what's the maximum area that you can get by building a rectangular field along a river like this with 2,400 feet of fencing? You could just do the length times width with 600 times 1,200. And I got 720,000 square feet. So just in case the problem asked for something like that, you could find it, right? That's the area of that rectangle. But we answered what it was asked. Okay. So we've got another problem. This next one is not about a rectangular field. It's going to be a different kind of optimization. Example 2. I'm going to walk us through this one also. I'm going to have you try example 3 on your own. All right, example 2. A cylindrical can. Cylindrical can is to be made to hold 1 liter, and in parentheses it says 1,000 cubic centimeters of oil. Find the dimensions. I guess a lot of these are like find the dimensions problems. I guess those are the ones that I like. Find the dimensions that will minimize the cost of the metal to manufacture the can. So there's no picture provided. That's the entire problem. No picture. So what information is given here? I guess we're given that it's a cylinder. We're given the volume that it's supposed to hold. And that's it. I mean, I guess there's some other things that we can kind of, that are kind of implied from the problem. Like it's a hollow cylinder. The metal is probably very thin. I imagine like a can of oil that it's made from thin sheets of metal. So what we're going to do is we're going to assume that the thickness of the metal is not really a factor here. That in order to minimize the amount of metal used, we want to do something about what shape this cylinder is. Here's what I'll do. I'll draw a picture of a cylinder. So it says, what are the dimensions of the can? So what dimensions would you say matter for a cylinder? Well, the radius matters and the height matters. So I'm going to label them R and H. And I guess they would be measured in centimeters because this problem already mentioned centimeters. So we'll keep that in mind for our final answer. That I think it's going to be in centimeters. You can imagine, I won't draw all the different scenarios this time, but you can imagine making a can that's sort of very, a cylinder that's very short and flat, or you could make one that's very thin and tall like a pencil. So there's lots of different ways to make a cylinder that could hold 1 liter, but there is going to be one way that minimizes the amount of metal used. Now, I think to minimize the amount of metal used, it feels like we're talking about surface area. The surface area of the can. If this is a hollow can and, I said the thickness is kind of not really a factor. So what I'm going to say is note, a cylindrical can is made from 2 circles and 1 rectangle. Can you see that it's made from 2 circles and 1 rectangle? I'll show you how. First of all, imagine I have this can and I sort of unwrap it. Well, you've got the top of the can. Here's the radius R. We'll call this the top. The bottom. All right, so where does the rectangle come in? Well, imagine the sides of a cylinder. If you were to, usually if you look at like a metal can of vegetables or something, a lot of times there's kind of, you can see a seam where the metal was fused together. You can imagine unwrapping it. So let me try to make a picture here. Drawing three-dimensional pictures is always tricky, so give me a second here. All right, so let's say these are the sides, like the unwrapped cylinder, that if you were to close this up, you would get the cylindrical can, and this plus this plus this, the sides plus the top plus the bottom equals the entire can. And I claim that if you were to unwrap this and just kind of flatten it out on a table, it would be in the shape of a rectangle. And, well, what are the dimensions of this rectangle? I guess this would be h. The height of the cylinder is the height of the rectangle. What about this curved part? I mean, I guess the curved part seems like it's sort of the circumference of the circle. So this length equals, do you remember the formula for the circumference of a circle with radius r? It's 2 pi r. Now, so I think that's good that we kind of deconstructed the cylinder. At this point, we should write something else. There's something else that was given that we haven't really written in our work yet. The 1000 is the volume. Now, the volume of a cylinder follows the formula pi r squared h. Volume of a cylinder with radius r and height h. We're given that this is supposed to be 1000. And right here, I'm not going to write the units. As long as we write the units in the final answer, I'm happy with that. So this pi r squared h is 1000. And I claim that we want to minimize. In order to minimize the cost, we want to minimize the amount of metal used. In other words, we want to minimize the surface area. I'm sort of assuming that the metal is already thin and we can't make it any thinner. So what's the surface area of a cylinder? Is that like a formula we're supposed to memorize? Not really. We could actually figure out the surface area by looking at what we wrote here. We said the surface area of the entire cylinder would be the area of this circle plus the area of this circle plus the area of this rectangle. By the way, I'm using the word circle. I guess technically we should use the word disk, because this would be like a shaded in circle. If you want to be technical, it's not just an empty circle. It's, that's all metal, right? So we're talking about the area of a disk. All right, so I say that the surface area, which I'm going to use capital A, is the area of the top, which is pi r squared, plus the area of the bottom, which is pi r squared. Here, we'll label these as we go. Top, bottom, plus the surface area of metal used to make this rectangle. This rectangle, which has dimensions h by 2 pi r. So 2 pi r h. We'll call that the sides of the can. And if you add up all of that, that would be the surface area, of metal used on the outside of the can. Let's think back to the guidelines that I mentioned earlier. Are we following those? Well, it said to draw a picture if you think it'll be helpful, and yeah, we did. We drew a diagram. It said introduce a function and variables. We've done that. This is a function. I guess the variables are r and h. We chose symbols that make sense for what they represent. Oh, the next thing on the guidelines says try to write the function in terms of one variable. This is written in terms of two variables because this has r and h. So I'd really like to get a just in terms of one of them. I think it would be nice if we could get this just in terms of r. Now, technically, you could do this just in terms of r or just in terms of h. But I think we should go with getting it in terms of r because r appears more in more places, like r squared, r. Let's go with that. H only appears once. So do you see anything that we can use to help get this just to be in terms of r? Yeah, we've got something we can use. This thing up here. Pi r squared h equals 1,000. It means that h is 1,000 over pi r squared. So we just got h in terms of r, and now we can put that into the function, the area function. And let's write this function here. So we want the absolute minimum of the function. And the function is a. And I'm going to write it just as a function of r. So I'm going to write a of r. Remember, this is not a times r. This is a of r. Like when you do f of x. It's that kind of notation. And we could write it as, well, when you add the top and bottom together, pi r squared plus pi r squared is 2 pi r squared plus 2 pi r times this thing that we just found for h. That's the function that we want to minimize. Maybe we could simplify it before we try to find the derivative, though. Yeah, we should. Like, we want to find a prime and critical points and all that. But look what's happening here. We've got a pi r. We could also combine the 2 times 1,000. So I rewrote this as 2 pi r squared plus 2 times 1,000 is 2,000. The pi's cancel out, and I'm left with just r on the bottom. All right, so I trust that you are able to find the derivative of this by now, so I'm going to just go ahead and write what the derivative is. We've been doing derivatives for so long. Just keep in mind that pi is a constant. Pi is just a number. You don't do anything weird with pi. You just treat it like a number. It's around 3.1, so 2 pi is a constant. That's going to stay out front. It's going to get multiplied by this 2 that comes down, so we're going to get 4 pi r. And then for this part, we get minus 2,000 over r squared. Well, okay, we want to look for critical numbers. Critical numbers happen when a prime is undefined or when a prime of r equals 0. Now, here's the thing. I do see an r value where this thing would be undefined. That would be if r is 0. However, I'm not going to put that down as a critical number. Do you know why? Why is r equals 0 not a critical number? Because I don't think r equals 0 can happen. I don't think we could have a radius of 0. It wouldn't be a cylinder, would it? Like, what would the shape look like if the radius is 0? So I actually think that a radius of 0 would be considered not in the domain. So I'll mention this off to the side. that the domain should be r greater than 0, right? We can't have a 0 radius. We also can't have a negative radius. So now when it comes time to find critical numbers, I don't think 0 should be considered. I don't think it's possible that we're going to say the answer involves a radius of 0. So we're going to try to set this equal to 0 and see if we get some other r values. Okay. We want to solve this. What's the best way to solve this? I guess there's more than one way to do the algebra. Here, I'm gonna do this a little differently than how I did it in my notes. I'm gonna say let's add the 2,000 over r squared to both sides. It's okay to divide both sides by r because I know that r is not 0. I could also divide both sides by 4. How about let's divide both sides by 4 first. Okay. Wait, now that I think about it, we don't want to divide both sides by r, do we? That wouldn't, I mean, we're allowed to do that, but what we really want to do is multiply both sides by r squared. So let's say pi r cubed equals 500. We're trying to solve for r. So we get r cubed is 500 over pi. So I'm getting that r is the cube root of 500 over pi. Well, that's a weird looking number, but it is a number. Is this an r value where a minimum occurs? Well, can we even figure out, like, roughly in our head what this is? If we say pi is around 3.1, so 500 over that, what's that going to be? A little over 150? Let's say it's around 150. Let's say this is like the cube root of something around 150. And what's the cube root of something around 150? Well, I know that the cube root of 125 is 5. Maybe this is 5 point something. Let's set up a sign chart with this number. So what was all that discussion I was just saying, where I was saying, I think that this is 5 point something. I did that in my head because I said 500 over pi. Maybe it's like roughly 150. You know, that's a little bit bigger than, the cube root of that's going to be a little bit bigger than 5 because I know the cube root of 125. The point is, I needed to know roughly what this number is so that I could check something to the left and something to the right. That's all. So if I think this is around 5 point something, then maybe I can check something like r equals 1 and r equals 10, and I'll be confident that I have chosen something to the left of it and something to the right of it. So that's what I'm doing here. Let's check a prime, a check. Let's use those values, actually. A prime of 1. Here's a prime. 4 pi minus 2,000 over 1. So, yeah, this is definitely negative. Let's check a prime of 10, because I think then we're getting something that's to the right of it. 4 pi times 10 minus 2,000 over 10 squared. Is this positive or is this negative? We need to go a little further to check, don't we? Let's make it 40 pi minus, this is 2,000 over 100. Oh, look at that. 40 pi minus 20, that's positive. So that was good enough for us to find that this is negative and then positive. So the function is decreasing and then increasing, which means that, yes, we have verified that this is where a minimum occurs. That's what I wanted to see. I wanted to verify that, yes, this is where a minimum occurs. So you don't have to know exactly what this weird number is, but you need a rough enough idea so that you are confident that you're checking something to the left of it, something to the right of it. Remember, we said the domain is r greater than 0, so don't check 0, but checking something like 1 is okay. If you wanted to be extra safe, if you're like really not sure what this number is, you could probably check 1 and like 100, I guess. Here, let's actually check. I'm going to check on my calculator, see how close I was. When I said I think this number is 5 point something, we can find out. Wait, we're going to go 3 cube root of 500 over pi. I actually don't know. Oh, look at that. There we go. So I thought it was 5 point something. It's 5.4 something. So yeah, that's the idea, is just in your head, you can figure out rough enough idea. And even if you weren't as close as I was, if you just said, I think this is maybe around 4 or 5 or 6, helps you figure out what values you need to check. Something to the left of it, something to the right of it. Okay, well, we're not done, right? I mean, we verified that this is the correct radius. So we've got half of the answer. The question was, what's the best shape to make the cylinder? The cylinder has a radius and a height, so we need to figure out the height. All right, so now find h. Like I said in the previous problem, you usually have something on your page already that'll help you find h, or find the other variable. I'm going to move the page up just for a sec to show you. And boom, there it is. H equals 1,000 over pi r squared. Let's use that. We already have h in terms of r. All we have to do is h equals 1,000 over pi r squared, but we have to put in this weird number that we found for r and then see if we could simplify it. So, all right, well, let's do it. Here's r, cube root of 500 over pi squared. I don't want to leave it like that. I think we can probably try to simplify. We'll try to simplify this. What can we do about this? Well, we have a cube root of something and it's getting squared. So one thing that you could do is you could write it as 1,000 over pi times 500 over pi to the 2/3. So I used a little property of exponents there that says if you're squaring something and you're doing a cube root, that's the same as raising it to the 2/3. Now that I'm looking at it this way, I see a pi and a pi, pi and pi, and I'm thinking maybe we can't just cross those out, but maybe there's something that we could do with them. So here's an idea. The numerator is 1,000. The denominator is pi times. When you raise a fraction to a power, you can do that to the numerator and to the denominator, right? So we could write this as 500 to the 2/3 times pi to the negative 2/3. The reason I did that is because I'm about to combine the pi's. This is all kind of algebra right now. Maybe I shouldn't be spending so much time on like simplifying things, but simplifying your answer is a good thing to do. Pi times pi to the negative 2/3 is pi to the 1/3. But also, what can we do about this 500? Because now that we wrote it this way, I see 1,000 and I see 500, and I'm like, well, 1,000 and 500, they should probably go together in some way, right? Because up top, the 1,000 could be thought of as 2 times 500. And then on the bottom, we've got 500 to the 2/3. So this is 500 to the 1. This is 500 to the 2/3. So I claim that we can write this as 2 times 500 to the 1/3 over pi to the 1/3. And an even nicer way to write that is 2 times the cube root of 500 over pi. So I think this is simpler than what we had up here. That had a fraction with a fraction inside it, with a fraction with a cube root of a fraction squared. That was messy. This is about as simple as we can make it. So let's answer the problem, the optimal dimensions. This is a cylinder, and we want to build this cylindrical can with the least amount of metal possible. We found, let's just say radius should be, we found third root of 500 over pi. We'll say it's that many centimeters. And the height of the cylinder, we found that to be 2 cube root of 500 over pi. And the height is also in centimeters. So that is the best shape that you could make this cylinder, to hold 1 liter while using the minimum amount of metal. Any other shape that you try to make this can is going to use more metal and be wasteful and cost you more. This is the most efficient way, the optimal way to make the shape of the cylinder. And the reason why I was so picky about simplifying H, maybe now you can see why I was so picky about it, is because I really like this result. That we can see that in the result, the height happens to be twice the radius. So I guess, can you imagine a can where the height is twice the radius? Let's try to do that. There's the radius. Let's go like one further. Okay, so that is sort of the best shape. Something like that. And, I think if you look at cans that are sold of, I don't know if you look at a 1 liter can of oil, but how about like a can of paint, like a 1 gallon can of paint? What kind of cylinder does it usually look like? It usually looks something like this, right? So yeah, there's a reason why cans of vegetables and cans of paint and cans of oil, there's a reason why they make the cylinders with certain dimensions. They do it so that they can contain the amount of volume that they want to contain while using the least amount of metal. So that's pretty cool. It's a way to save costs. And I mean, it's also ecologically the best thing to do, to use the least amount of material. You don't want to be wasteful. I will point out that there are certain types of cans that don't fit this shape. Like cans of cat food are usually very flat. And those are cylinders, but they're usually very flat. And you could say, well, why are they not using this shape? And there's, other factors to consider. I guess with cans of cat food, they make them very short and flat because they want them to be able to stack nicely. So actually, they're a little wasteful on how much metal they use. And then other types of cans, like a can of soda, would be usually taller. And that's because they want to make like a nice grip that you can hold in your hand. So not every metal can will be these dimensions, but when you're doing something like a can of oil or a can of paint, and you're not really concerned about the aesthetics so much, then yeah, this is the best shape that you can make. My wife and I have gotten some cans of paint recently for our house, and like a big a big tub of stuff to stain our deck, and you get like a 5-gallon cylinder of something, and it still kind of roughly has this shape to it where the height looks like it's twice the radius. This problem was about a 1 liter. I guess I haven't really specifically said this, but this problem was about a 1 liter can of oil. But if you're talking about like a 1 gallon or a 5-gallon, you get different numbers, but you still get this same pattern where the height is double the radius. Now that's for a cylinder that has a top and a bottom. I guess like an interesting variation of this problem would be to give you a problem like this, but maybe where the can has no lid. That's kind of interesting. That would change everything. In fact, that might change the answers, right? Both of them. I'm going to give you a problem to try. I want to just point out one thing before we do that, is in the 2 problems we've done so far, where is the result from the first one? I just want to show you something. This was the answer to the first problem, 600 by 1200. And I guess I want to say that it's kind of a coincidence that in both problems we did, one of the dimensions was twice the other. That's not always going to happen. It happened with the cylinder. It happened with the rectangle bordered by a river. All right, but you can't always count on that. If it's a problem about dimensions and you find one of them, you can't just multiply it by 2. That might not always be right. All right, so where were we? Let me give you a problem to try. This is going to be one about a different shape. It's also about dimensions, I guess. So example 3. The word problems we're doing in this section, they kind of take a while, so we're not doing a ton of them. But you'll also get some homework problems for practice. All right, a Norman window has the shape of a rectangle surmounted by a semicircle as shown. So this one is going to provide us with a picture. If the perimeter of the window is 30 feet, find the dimensions of the window so that the greatest possible amount of light is admitted. Now wait just a moment, because this problem is going to provide us with a picture. So you're going to want to see that. So it's a window in the shape of a rectangle surmounted by a semicircle, and I thought that it would be nice to provide a picture, because what does a rectangle surmounted by a semicircle look like? So you've got some kind of rectangle, and this problem is actually going to label some of these sides for us. This is going to be X and Y, and at the top of it is half of a circle. And the half of a circle has a radius. I'm going to label the radius for you, but I actually feel like I don't need to. I feel like you could figure it out on your own. So real quick, before we do the full problem, can you figure out what the radius of this semicircle is? Like, what's this length of this little line segment? Well, it would be the same as this, which would be half of this, right? Half of this. So it's going to be x over 2. But I'm giving you that. All right, so this is the problem. I'd like you to pause the video, spend a few minutes, and see if you can answer this. So as I work on writing the solution to this, I'm going to have to probably move this problem away, but I think we've all got it in our notes by now. And, you know, it's labeled, so I don't need to draw another picture of it. If you tried working on this and you weren't sure where to start, you know, keep in mind that the problem says something about perimeter. You could try to come up with a formula for perimeter. We're trying to let in the greatest possible amount of light, so I think we actually want the greatest amount of area. So, you know, see what you can come up with for perimeter and area. Well, I'm going to go ahead with it. The perimeter of this window is given to us as 30. But moreover, I think we can actually write it in terms of x and y. Because looking at the picture, the perimeter would be, you know, here's x plus y plus the perimeter of the semicircle part plus another y. So I'm going to write this as 2y plus x plus, what's the perimeter of the semicircle part? It's half of the circumference of a circle. So it's going to be pi times the radius, x over 2. The area, what's the area of this entire window? It's a rectangle plus half of a circle. So the rectangle is xy, and the half of a circle is 1/2 pi r squared. So 1/2 pi r squared. We're trying to maximize area. So that's going to be the function that I'm interested in finding the maximum of, the area function. Right now it's written as a function with 2 variables. So of course we want to write it in terms of just 1 variable. And because x appears in multiple places, I think we should try to get this just in terms of x. Well, in order to get this in terms of just x, I'm going to take this stuff up here and try to solve for y in terms of x. So I wind up with y equals 1/2 30 minus x minus pi x over 2. Or another way to write that is 15 minus x over 2 minus pi x over 4. This is y in terms of x. Oh, you know what? Actually, before we actually plug that in, let's simplify this a little, because there's a 1/2 and then there's a 1/2 squared. So this is xy plus 1/8 pi x squared. If you don't see where the 1/8 came from, remember that when you square a fraction, you square the top and the bottom. So the x over 2 squared winds up with an x squared up top and a 4 on the bottom. The 4 on the bottom got multiplied by the 2 to become an 8. So that's where the 1/8 came from. All right, so we want to find the maximum. In other words, we want to maximize the function. The area of x equals x times, let's put this in for y, plus 1/8 pi x squared. Oh boy, that's the function we need to work with. Well, it's not that bad. I mean, we can actually rewrite it let's rewrite this before we try to find the derivative. Let's distribute the x. Because I think if we distribute x, I don't know, maybe there's something that's going to combine with this term. Maybe, looks like. So let's see what happens. This is 15x minus 1/2 x squared minus, I'm going to go ahead and write these as fractions. Like the 4 on the bottom, I'll just make it 1/4. 1/4 pi x squared plus 1/8 pi x squared. Yeah, we can combine some terms here. You see what I mean about we can combine terms? We have a minus 1/4 x squared and a plus 1/8 x plus 1/8 pi x squared. So this is 15x minus 1/2 x squared. And then what do these two terms combine into? It's going to be minus 1/8 pi, or you could say pi over 8 x squared. So this is the function that we want to maximize. We want the most possible area to let in the most possible light. Let's find the derivative. You know, in a way, I feel like when you start finding the derivative, that's where the calculus part of this problem really begins. So, yeah, a prime. A prime. So we've written it in this nice form, so it's not so bad to find the derivative of it. Oh, you know what? Actually, there's an x squared here and an x squared here. We probably could have combined these two, like factor out an x squared from these two terms. We could have done that. Anyway, this is 15 minus, bring down the 2. We're going to get x here, and then minus, the 2 comes down. There's an 8 on the bottom, so pi over 4 x. So what I'm saying is, like, we can combine the x here. Okay, that's the derivative. We're looking for critical numbers. I don't see anywhere where this is undefined, so let's set it equal to 0 and solve. So maybe you rearrange it and you get like x times 1 plus pi over 4 equals 15. And then you say, oh, I'm just going to divide both sides by that part that's in parentheses. So you get 15 over 1 plus pi over 4. It seems like in a lot of these problems, we're only finding one critical point, and that one critical point seems like it usually winds up being the correct answer. And that's probably what's going to happen here, but we should still check. We need to figure out, is this really a maximum? So before I do that, I'd like to actually rewrite this another way. You know, I often say that I'm not a big fan of leaving something with a fraction inside a fraction. So how could we get rid of it? How could we get rid of the fraction inside a fraction? Here's my idea. Multiply by 4 over 4. Why am I multiplying by 4? Because that's the denominator of this bottom thing. That's going to rewrite this as 60 over 4 plus pi. And I think that's a little bit easier to work with. Okay, we want to verify. This is where a max occurs. We want to verify this is where a maximum occurs. So, okay, again, we're in this situation where we want to try to estimate what is this number. I'm glad I simplified it because I could work with this. Pi is a little bit bigger than 3. So 4 plus pi is a little bit bigger than 7. 60 over something that's approximately 7 gives me a rough enough idea, okay? I'm going to say that this is roughly 60 over 7, which is roughly equal to 9. Now, it's not exactly 9, but that's close enough that I can check something to the left and something to the right, and That's really what matters. So in my little sign chart here, I'm going to put 60 over 4 plus pi. I'm going to put a prime and a, and we're going to check. We're checking x values. I guess, again, I feel like x has to be positive. Looking at the diagram, looking at the picture, x can't be 0, or x can't be negative. So let's check a prime of 1. That's definitely to the left of 9. So we could check that. 15 minus 1 plus 1 plus, there. Using this form, I plugged in x equals 1, and I get something that's positive. And then I also checked a prime of 10. You could actually go with something a little bit larger if you just really want to be confident that you are to the right of this number. You could go with a bigger number, but 15 minus 10 times 1 plus pi over 4. I did this, and I found that this was negative. So my sign chart goes plus, minus, so the function is increasing and then decreasing. And then I check, like, is that what I wanted? Increasing and then decreasing, yes, that means that there is a local maximum at this x value. And because it's the only maximum that we found on the domain, the function never goes back up to increasing, this is going to be where the absolute max occurs. So what's left? We found x. We need to find the other dimension. We need to find y. So now find y. All right, so this over here was us verifying it's a max. Now we'll find y. I always say that usually there's something on your page that helps you find the other variable. I'm going to move the page up, and I'm going to show you where it is. All the way up here. Y equals, and it's in terms of x, and we could use either one of these. I'll probably use the second one. We said y equals 15 minus x squared minus pi x over 4. So I did put in this 60 over 4 plus pi. I got 15 minus 60 over 4 plus pi over 2 minus pi times that. Yeah, we're going to simplify this. I'll skip some of the fraction arithmetic right now, and I'll tell you that I found that this simplifies to 30 over 4 plus pi. All right, finally, we can write the answer. Answer. The dimensions of this window. You can look back at the diagram and say, yeah, we found x, we found y. How should we write this? I guess, oh, you know what? You know what we can do? Because the picture was provided with the problem and the picture was labeled with x's and y's, we can just say the dimensions of it are x equals this many feet and y equals this many feet. Because the problem gave us x and y to work with, so that's, yeah, we'll just give the answer in terms of x and y. All right, so that problem took about 1 full page. I think I've got one more problem for us. So we've done 3 big word problems today. I think examples 2 and 3 were probably the hard ones. I'll show you one more, and I'll walk us through this one. It's a little different, but I think that this last one is not really that bad. So example 4 of an optimization word problem. It says, find 2 positive numbers, 2 positive numbers whose product is 100 and whose sum is a minimum. You know what? I'll leave it up to you. If you would like to, you could pause and try to do this one, or you can just wait and I'll do it for us. This is going to be a little bit different because there's not really any diagram that we can draw. This is not a problem about shapes. That's what makes this one different. You know, examples 1, 2, and 3, they were all about finding the best dimensions of some kind of shape. And I wanted to make sure that I showed you one optimization problem that was not like that. It's still about finding a minimum. I don't have any kind of drawing of this scenario that I could give you. So, two positive numbers. I think we should label them. Let's say that they are called x and y. If you call them something else, if you call them a and b, that's perfectly fine. We know that their product is 100. xy equals 100. And we want to minimize their sum, x plus y. If this is the function, this is, written in terms of two variables, so we want this just in terms of one variable. We're not going to differentiate it when there's two variables. Since xy equals 100, we could say y is 100 over x. So the function to minimize is, let's give it a name. I didn't give it a name up above. I mean, it's a sum. Do you want to call it s? We could call it s. I actually, on my page, this time I called it f of x. Just for old time's sake, let's go with an old-fashioned f of x. Why not? It's x plus y, but we're writing x plus this. It's all in terms of x. I'm going to say where x is positive because the problem told us that x and y are both positive numbers. It says find two positive numbers. So let's find the derivative of it. The derivative of f is 1 minus 100 over x squared. This is what I'm looking for critical points of. I can't really say x equals 0. Even though the function would be undefined, like the derivative would be undefined. So it's tempting to call that a critical number. It can't be a critical number because it's not in the domain of f. It's not in the domain of f because it said x and y have to be positive. But anyway, I don't think that 0 would work because I don't think that 0 times anything is going to get you 100. So let's look for other critical values. Let's set this equal to 0 and solve for x. So I guess we get 1 equals 100 over x squared. So x squared equals 100. When you take a square root of both sides, usually you do plus or minus the square root symbol. But I'm not going to do that because I know that x has to be positive. So this is just positive 10. This is the only critical number, so this had better be it. I mean, we don't have any endpoints of an interval of like a domain to check or anything like that. So, this should be it. Yeah. Here's 10. F prime F what should we check? Let's just check 1 again. 1 is pretty easy to check. F prime of 1 is 1 minus 100 over 1. This is definitely negative. We need something to the right of 10. What would be an easy number to go with? Well, let's just, I don't know. Let's do 12. So 1 minus 100 over 144. I can tell that that's 1 minus something that's 1 minus 100. What am I trying to say here? 100 over 144 is less than 1, right? 100 over 144 is less than 1. So 1 minus something that's less than 1 is going to get you a positive number. That's what I was trying to say. So this is negative and then this is positive. So the function was decreasing and then increasing. So yes, I do think that as this function goes down and then goes back up, it does mean that we found a minimum. So we verified that x equals 10 does get us a local minimum. And we should find y because the problem said find two positive numbers. We called them x and y. We found one. We need to find the other. So, do we have something on our page that will let us find y? Absolutely. It's right here. Y equals 100 over x. Y equals 100 over x. So 100 over 10, which is 10. And we should write our answer. Let's just take a quick look back at the problem to make sure we're answering the correct question. It says find two positive numbers whose product is 100 and whose sum is a minimum. All right, answer. The numbers are 10 and 10. Those are two positive numbers. And you could kind of check that their product is 100. Can we check that their sum is a minimum? Well, the fact that their sum is a minimum is from all of this work that we just did. We verified it over here. So really this was the main part where we verified that that's a minimum. The sum, by the way, is 20. So that's the smallest possible sum that you could get from two positive numbers that multiply out to 100. Okay, so we saw 4 problems. 3 of them were about finding dimensions of shapes, and then this last one, the way the problem was phrased, it kind of seemed like a little brain teaser, like a puzzle. Can you find two numbers that do this? And there was no guarantee that they were going to be integers, but it looks like it turned out that they were. So there's other types of little problems like this about finding a pair of numbers with a certain property where something is minimum or something is maximum. All right, so we'll wrap things up here. So that was our section on applied optimization. So now we've seen some word problems that use the derivative to help us find the maximum or the minimum. It's sort of finding the best way to do something. The best shape of a rectangular field, the best shape of a cylinder, the best shape of a window. Or the last problem that we did, it wasn't really a shape, but it was still kind of the best or optimal way to do something, if you think about it. It was us trying to find the minimum possible sum. So the numbers that gave us the minimum of something. All right, anyway, that's it for this section. And next section we're going to jump to is going to feel a little bit different. So, I know we've been skipping around to some different things, but yeah, moving right along. And I hope everyone is doing well. So that's going to be it. I'll see you next time.